and started developing the general theory of rotation for arbitrary objects, non-rigid objects with internally moving parts, a swarm of bees being the extreme example that I have in mind. And I was beginning to set up that theory last time, and then of course the end of the story will be to apply that to the case of a rigid object and see that we recover all of the stuff that we had originally. So where were we? Torque. I have defined the torque on an object if I have a point P, and torque is always defined with respect to a particular point. With respect to a point P, if I have a force out here acting, maybe there's one of those B's is situated at this point, and it's out at a vector R from the origin, and a force is acting on it at that point, then the torque is equal to R cross F, the cross product of the vector from the point about which you're calculating the torques out to the place where the force is applied. That cross product, if you work it out, exactly reproduces force times lever arm, the old definition that we had started with. But it also assigns a direction to the torque. Angular momentum. Again, with respect to some point P, if I had a point P here, and I have a mass here at a vector distance r away, and it's moving along with a momentum little p, then the angular momentum of this mass with respect to the point P is L equals R cross P, where P is the translational momentum of V. You can't quarrel with those. Those are definition, the definition of torque and the definition of angular momentum. Now, what good are they? They give rise to a nice formulation of Newton's second law for rotations. Suppose I calculate the time derivative of the angular momentum, dl by dt, the rate of change of the angular momentum. What is that? Well, there are two terms in here. There's an r and a p, so I need to use the product rule for calculating the derivatives. First, the derivative of the first one, dr by dt, crossed into the second one, plus it's the first one crossed into the derivative of the second one. Somebody's thinking, wait a second, I understand the product rule for just an ordinary product of two functions, but this is the cross product of two vectors. Are you damn sure it still applies to cross products of two vectors? Yes, I am, because I checked it out. What these correspond to is a whole set of 6 different terms that involve a product of one of the components of this times one of the product of one of the components of that. So it is actually the product rule quoted 6 times over if you want. But the simple way to think of it is that the product rule for differentiation works just as well for cross products of two vectors as it would for the ordinary product of two functions. And the reason is that the cross product is nothing but 6 ordinary products, actually. So here are the two terms. What, on the other hand, is dr by dt? That's the rate of change of the position. That's nothing but the velocity of this object. And p, the momentum, is mass times velocity, of course. So let's look at the first term here. dr by dt cross p is nothing but d cross mv. The m is a scalar. I can pull it out in front of the cross product and write this as m times V cross V. What do you make of that?
V squared.
No, not V squared. If it was V dot V, then it would be V squared.
That's
It's V
zero.
cross V. Any vector crossed into itself gives you 0. It's a sine of the angle, and the angle is 90 degrees. The angle is 0. Excuse me. So this is equal to 0. The cross product of any vector with itself is equal to 0. So it so happens that the first term here is automatically 0 because it involves V cross V. How about the second term? Do you remember what dp by dt is? Rate of change of momentum, that's nothing but force. F equals dp by dt. In fact, this is the way that Newton himself wrote Newton's second law. Force is rate of change of momentum. Of course, this is d by dt of mv. And the mass typically is not changing, so it's m dv by dt, which is m times a. So there's the way which we nowadays write Newton's second law of motion, F equals ma. The way Newton preferred to write it is F equals dp by dt, but in any event, dp by dt is equal to F So the conclusion, dl by dt, in calculating the time derivative of L, the first term drops out at 0, the second term is r cross F. But what's that? Tau, Greek tau, it's the torque. So dl by dt is r cross F, or I'll put it up here, the grand conclusion, dl by dt equals tau. Or actually, let's write it the other way around so that it'll be a little more suggestive. Tau is equal to dl by dt. That's the grand conclusion. Tau torque is equal to the rate of change of angular momentum. That's exactly parallel to Newton's version of Newton's second law for translational motion, that force is the rate of change of translational momentum, torque is the rate of change of angular momentum in the same sense. So there's Newton's second law. For rotations, by the way, it's nothing new, right? I didn't have to invoke any new laws of physics here. I had two definitions. I took the derivative of this one, and Newton's the only law of physics that went into there was Newton's second law of motion for translational motion. That's the only input I used, and the consequence is that tau is equal to dl by dt. What does that tell me? Rotational dynamics got no new information in it. There's no new law of physics. It's only a useful way of rewriting or packaging some information that I already had from translational dynamics. I was under the misapprehension when I first studied this stuff myself, that rotational dynamics was a whole set of new laws. This is not true. It's all follows from the translational motion. There's nothing genuinely new in it. So there's Newton's second law for rotation. Suppose now that I had not just one object, but a bunch of objects. My standard example, swarm of bees flying every which way, and there are a bunch of forces acting on them, and each one's got a momentum and everything. I could add up the taus, the torques on each one of those bees, and the angular momentum of each one of those bees, and write this formula for all of them. Let tau total equal the sum of tau I, that just means the sum of the torques on each of the bees separately, and L total is the sum of the angular momentum. Sum of the angular momentum of all the bees considered separately. And then, because each tau is equal to, tau I is equal to dli by dt, it follows that tau total, add them all up, is dl total by dt. But, when this is just the sum of all the individual angular momentum, calculated always with respect to the same point, by the way. I'm implicitly using the same point for calculating torques and angular momenta, and torque and angular momentum for all the points that go to, all of these that go to make up that swarm. Now, when I got to the same point for the forces, I don't know if you remember this, we wrote down force total is equal to dP total by dt. And then it turned out that when you're doing this sum over all the forces, all of the internal ones cancel out. Remember that? We divided forces into two different types. The forces that were imposed on the system from the outside, like gravity or whatever, and the internal forces that are the interaction of each particle with some other particle in the group. When you added over all the forces, the internal forces dropped out. Is the same thing true for torques? Yes, it is, but there's a subtle twist on here. In the sum, internal torques internal torques cancel out. Why is that? Well, let's think about two particles in there, particle A and particle B. And here's the reference point P. And so here's RA, the vector out to A, and RB, the vector out to B. Now, imagine the forces. The force on A due to B, let's call that just F sub A, the force on A due to B, and the force of B on B due to A. We know that those two forces are equal and opposite. That's Newton's third law.
But they need to be along the line.
But they must act also along the line joining them if their two torques are to be equal to 0. Newton's second law, very simple point. Newton's second law says that the forces are equal and opposite. The force of A on B is equal and opposite to the force of B on A. But that doesn't necessarily mean that they act along the line joining them. I could have a situation like this, where the force on B acted like that, and the force on A was equal and opposite, acted like that. Would those torques cancel out in that case? No, they would not, because the torque on B would be 0. It's acting right through that line. The torque on A is not 0. The lever arm is non-zero. But if we pump up Newton's third law, what some people call the extended or the strong form of Newton's third law, to say not only that the forces are equal and opposite, FB is minus FA, but also that they act along the line joining the two. So back to the picture that I originally drew, where those forces not only are equal and opposite, but also point along the line joining the two here. Then I think it's pretty clear, the line of forces is equal for both of them, and therefore the lever arm is the same for both of them. So in that case, I've got equal and opposite torques, and the internal torques cancel. But there is this slight subtle twist here. I have to take not just Newton's third law, but a little bit more than Newton's third law, the extra assumption that they act along the line joining the two. Of course, this is going to be normally true. I mean, if you're talking about gravitational forces, those of course act along the line. Electrical forces, those act along the line joining the two. But you could conceive of a kind of complicated force structure that obeyed Newton's third law in its original form, but not obeyed the extended version of Newton's third law. If you come across forces of that type, then what I'm about to say does not hold. But if we believe for forces that obey the extended version of Newton's third law in this sense, then the internal torques cancel out. I didn't say that very well, but have you followed the argument? Kind of a subtle point. Yeah, Herb.
Are those what are called central forces? The ones
Central forces, why not? Yes, central force, so the force on A due to B is central in the sense that it acts through the center of the source force. Good word for it. Yeah, central forces. As you'll find out next semester, probably magnetic forces are not always central forces, not typically central forces, and that makes a little bit of a problem with this argument.
But what about the example you gave us of a small wheel contacting a big wheel by friction? Should I not have asked that?
No, you should have asked that. Somebody else should have asked that. Because I said, you know, there's no Newton's third law equivalent for Newton's third law. You know what I was doing secretly there? I was using a different reference point for the two torques because it was the obvious thing to do in that context. You remember that where I have one wheel rubbing up against the other wheel, and then the forces were equal and opposite. And I said, but the torques are obviously not equal and opposite because the lever arm is different in the two cases. I was actually doing what was natural in that problem, but I was implicitly using a different reference point for torques here than over here. If I had said, yes, use the same reference point for both of them, that would have been kind of funny because I'm using the center of this circle for the torque acting on this one. But in that case, Newton's third law would hold for torques. How about that? So there is a certain sense in which Newton's third law does hold for torques too, but it's kind of a misleading sense. I would say.
Yeah, in other words, it was natural when you described that to us because we were looking at these two as solid bodies that we were going to solve for, like the isolated bodies that we did in linear motion.
Precisely.
But because it's rotational, we're solving for how this force spins this object, the one on the right, and how the downward going force spins the one on the left.
Right.
And in that case, you want the torque on the object about its center, which is really the parallel to the force on the mass in the isolated body.
Right.
That we studied.
Catch that? Done beautifully.
Well,
that's exactly the point. If you're talking about a rigid object rotating about a fixed axis, then the natural thing to do is put your P, the point about which you're calculating torques and angular momenta, on that axis, of course. That's what it's rotating about. It's awkward to put it anywhere else. But in the general case where you've got a swarm of bees, there is no natural place to put that the point P. So, and in this theory, I'm sticking the point P always at some fixed location and staying with it. So, yes, in a sense, I am using Newton's third law for torques here. Newton's third law for torques, which applies with the extended version of Newton's third law, provided that you calculate all your torques about a full point. Very subtle, very subtle. But what's the long and short of all this? The long and short is that the internal torques cancel out in pairs, and all I have to worry about is the external torque, as was the case for forces. But it's a little bit slipperier than that case. How external is dL by dt, dL total now. So the rate of change of the total angular momentum is ordinarily equal to the total external torque acting on a system, and you don't need to worry about internal torques. A good thing too, because if you've got a big object with 10 to the 23rd particles that go to make it up, you don't want to have to be worrying about all of the internal forces between those particles. You'd like to talk about what's the external forces that are acting on the whole object, just on the object as a whole. So, how about now we specialize this to the case of a rigid object. a rigid object. There it is, a sphere, for example. How does all of this apply to a sphere? What would the total angular momentum of that sphere be? Well, let's see. That's the sum of the angular momentum of all the little bits and pieces that go to make it up. What is the motion of a particular piece of that sphere, or whatever this object is? That little piece goes around in a circle as the whole object rotates with angular velocity omega, isn't that right? Each point goes around on its own circle. Of course, that circle is kind of small. A point out here on the equator is going around a large circle, and a point down at the South Pole is going around on a tiny little circle as they rotate. Do you remember what the angular momentum of a particle going in a circle is? You can get it from the general formula. Let's see, R cross P is R times mv, and in magnitude, that's it, because if it's going around in a circle, R and mv are perpendicular to each other. R cross mv points perpendicular to the circle, and its magnitude is the radius of the circle times the linear momentum, the translational momentum of the point out of radius r. So this is the sum of Ri, Mi, Vi, where Vi is the, I'm talking only about the magnitude here. All of the angular momenta are going to be pointing in the z direction, in this case, in the same direction perpendicular, along the line of the axis. RMV made that sound more complicated than it was supposed to be. Momentum, the angular momentum of a particle going in a circle is RMV. Add it up for all of them, sum of the RMVs. But what is the velocity of a point here if it's out at radius Ri and the whole thing is spinning at an angular velocity omega? Can you remember the connection? It's proportional to how far out you are, and the proportionality factor is exactly omega times r, isn't that right? So if it's a rigid object, here's where the rigid object comes in, is that there's one angular velocity for the whole works, and the velocity of any point in there is proportional to how far it is from the axis with a proportionality factor omega. We look dubious about that. Remember how we did that originally? Arc length and theta and the radius. Theta, the angle and radian measure, is arc length over r. Differentiate, you get omega is equal to the derivative of s with respect to time. Differentiate with respect to time. That v over r. That's what I'm using here. V is equal to omega times r. So, what is this? Sum of Ri, Mi, omega times Ri. Omega, however, is the same for all the points on there. That's just the angular velocity of the whole object. That comes out in front. Omega times the sum Mi Ri squared. Do you happen to remember that sum? Recognize that sum? What's that? Mi Ri squared is the sum summed up is nothing but the moment of inertia of the object. That's I, so I get I times omega. There's the connection. L total for a rigid object, the total angular momentum is the moment of inertia of the object times omega. That was on my dictionary there. It corresponds to P equals mv for translational motion. Here it's L equals I times omega. Suppose that I stuff that into the general formula there, then tau is equal to, I won't write the external on there, it's whatever torques are acting on this rigid object, is the rate of change of L, but L is itself I times omega, so this is d by dt of I omega, which is I not changing, if this is a rigid object, the moment of inertia is fixed, but omega is changing, the omega by dt, which is alpha, the angular acceleration. What's the conclusion of that? For a rigid object, tau is equal to I times alpha. That's Newton's second law. In the version that we used at the very beginning, I motivated it then just by saying, well, it's kind of like the second law, F equals ma. Here it's tau torque equals I times alpha. Now I have justified it. Actually, if you watch this argument very carefully, as I was saying earlier, everything followed from translational dynamics. There's no new laws in here, but here is the rotational form of Newton's second law of motion as it follows from Newton's second law of translation.
And
All right.
actually, logically, I think, but much harder for learning. This is where I turns out to be so important. When you do this calculation for a rigid body, you see that the one thing that characterizes the whole dynamics is that sum. And that's the real motivation. This calculation is the real motivation for all that stuff we did on I. It's important.
Absolutely.
So if you're given to logical and mathematical thinking, you may have been a little bit confused that you're doing all those things about I, and we're only kind of
Indeed. Logically, I presented this subject backwards, and but I don't know pedagogically. I have a hunch that it's the cleanest way to do it pedagogically. I talked about rigid objects first. What is the analog to mass? I made some argument that it depends on where the stuff is, and motivated mr squared for moment of inertia. But that was logically kind of sloppy. I mean, I hope I made it plausible, and we did some examples and then calculated a lot of moments of inertia and stuff like that. And then we came back to the fundamental theory. It would be much more logical to start out with tau is r cross f. L is, do this argument at the very beginning. At the end of it, I would have derived the formula for moment of inertia. At this point, I would say, let's define this quantity as moment of inertia, and done everything in the other order. In other words, start with the general case and proceed to the special case of rotation of rigid objects. I think that that's logically a better way to do it. It somehow or other, this argument I've given today is, in my mind, rather subtle and opaque. So I don't like to rely on that when I'm trying to establish people's intuitions about it. However, I think logically it is kind of backward. By the way, you'll notice that all of the books nowadays do it sort of halfway. The books motivate the formula for I from the formula for kinetic energy. They say, let's figure out the kinetic energy of rotation of some rigid object, add up the 1/2 mv squared for all the points that go to make it up, and they get something that's of the form 1/2 I times 1/2 this sum times omega squared, and then they say, let's call that sum moment of inertia. That's maybe the quickest way to get your hands on moment of inertia, but it also strikes me as logically a little bit fishy, or at least logically convoluted. I don't know. Where are we? Let's do some examples. In fact, the classic example, rolling motion. I don't like to advertise physics too much, but I find myself doing it sometimes. If you talk to practicing physics teachers, they will very often they say, oh man, rolling objects down an inclined plane, how boring. If that's your attitude, I'm very sorry, because what you're about to see is, to my mind, one of the most beautiful arguments of the human mind. This is fabulous. It's not boring. But the theory of an object rolling down an inclined plane. Here it is. I would like to know, what's the acceleration of a rolling object by rolling? I mean, it's not sliding down. It's not, you know, that's not rolling, that's sliding. That's rolling. I'm talking about rolling today. An object rolls without slipping down an incline that's tilted as always at an angle theta. Question, what's its acceleration? More precisely, I guess, because different points on it have different motions. I mean, what's the acceleration of the center? Tell me, what forces act on this as it rolls down there? Gravity. Very good. mg. Normal force. You better believe it, otherwise it will be going straight down. Normal force. Friction. Huh? Who said anything about friction? Statement of the problem says nothing about friction. Oh, yes, it does. The statement that something rolls without slipping is secretly telling you there's got to be friction in this system, because if there was no friction, it wouldn't roll, right? It would just slide. If you made this thing out of ice and you had a perfectly icy surface here, why would it roll? It would just slide down there like a block of ice. The fact that it rolls is telling you not only that there's got to be some friction in here, but exactly how much friction there is. There's just exactly the right amount of friction to keep this thing from slipping. Look at this diagram here. What's the torque about the center associated with gravity? 0, right? Acts right through the center. What's the torque about the center associated with the normal force? 0. There is no torque except the torque provided by friction. If you're calculating with respect to this point here, friction is the only force in that picture that can give this thing some angular acceleration. So if I say it's rolling without slipping down an incline, I'm telling you there's friction in the problem. I never said it, but it's got to be there, otherwise it wouldn't have rolled. So those are the three forces acting. Newton's law, translational law, F equals ma, said how do we do this in the usual way? Here's the angle theta again. Down the plane, I've got mg acting. By the way, what kind of friction is that? Sliding friction or static friction? It's static friction. Yes, the thing is moving, but the point of contact is not moving. If it was slipping as it went down there, that would be sliding friction, but this is static friction. The point of contact is not. So all I know about the friction is that F is less than or equal to mu sub static times n. I don't know that it's exactly equal to mu times n. It's whatever it has to be, less than mu sub s times n to keep the thing rolling. So in the horizontal, down the plane, I have mg sine of theta pulling down the plane, and F pulling back up the plane. That's got to be the mass times the acceleration. That's the translational equation of motion. Two relevant forces acting, mg, or rather mg, the component of mg pulling it down, friction pulling it back up. That's the translational motion, but now I also have the rotational equation of motion. Now comes a choice, by the way. You could calculate torque in this problem about any point, any fixed point you care to. Some people like to use the point of contact here. Some people are really perverse, use a point like this one over here. Okay. I personally like to use the center of mass in all rolling problems. From my experience, it's the safest point to use. Actually, the center of mass is not a fixed point here. It's rolling down the slope. And it's kind of surprising that you can get away with using the center of mass at all. But the fact of the matter is, center of mass to the center of mass, which is to say the center of the rolling object, that's the safest way to do business. I'll tell you why. If you want to do torques about this, about the point of contact, you can do it that way. You'll get the right answer unless you screw up, but it's very easy to screw up. You know why? because the moment of inertia about the point of contact here is not what you're going to look up in the text. Text is going to give you the moment of inertia about the center. If you want to work your way down to the moment of inertia about the point of contact, you're going to have to remember to apply the parallel axis theorem to slip the moment of inertia down to that point there. You can do it and it'll work out, but it's a little bit more awkward because you had to transfer the moment of inertia. So I personally would advise you to use the center of mass, the center of the rolling object. Where are we? Of course, with respect to the center of mass, what do I have? The torque acting about the center? Well, you tell me. I never gave this thing a radius. Here it is. Its radius is r. So what's the torque about the center of that thing? It's the force times the lever arm. As I argued a moment ago, mg and n have no lever arm. They don't produce any torque. The only torque is provided by friction here. So it's F times the lever arm, which is R. That's the net torque acting on this thing. That's equal to I, its moment of inertia, times alpha, the angular acceleration. Here I have two equations. Well, that same force of friction is doing two things for us in this problem. In its role as a regular force, it is slowing the object down. It doesn't roll down here quite as fast as it would have if it had been sliding frictionlessly, because there is that frictional force holding it up. So it slows the translational motion down. It also produces rotation via the torque equation. I don't know if you're like me, but when I first saw this stuff, I said, wait a second, you're counting the same damn force twice. You used up that friction force in the translational equation of motion. You can't use the same force to do the angular equation of motion. That is simply nonsense. There is no law of conservation of force. The same force does play two quite independent roles here. It spins the thing up and it slows the thing down. Same force. Where are we? Folks, I'm trying to calculate the acceleration, but I see here that there are two equations in three unknowns. I don't know the frictional force, except that it's less than or equal to something or other. I don't know A, and I don't know alpha. Three equations, two unknowns, we're in trouble. What's the third equation? There's a relation between alpha and A, because as this thing, alpha is the angular acceleration of the wheel. A point on the circumference is moving with an acceleration. What is the connection? I started to do it here. Theta is S over R, omega is B over R, alpha is A over R. So alpha equals A over R. Okay, now let's put them together. I might as well work with this formula here. F is equal to, dividing through by R, it's I times alpha, which is A over R, and we're going to divide through by the R, so it's IA over R squared. Take that up here and stuff it into the linear equation, and I get mg sine of theta is equal to, pulling the frictional force over to the other side, ma plus IA over R squared. I'm going to divide by m and factor out the A on the right. A times 1 plus I over m R squared. Divide through by this factor to get A, and my conclusion is A equals G sine of theta over 1 plus I over m R squared. That's the formula for the acceleration of an object that rolls down an incline of angle theta. So that got squished, and I want to play with that formula, so I'm going to stick it up here. Did you follow this? I did the algebra a little bit quick because the physics was all on the table in those three equations. F equals ma in the translational mode, tau equals I alpha, rotational, and then the connection between alpha and A.
And there could be, in some cases, David, there could be a place where theta gets so steep.
But the friction can no longer hold it,
Right.
and you slip over to the regime of kinetic
And
friction.
that's nice, because the sine theta does increase with theta. Right? So there's a certain place where this equation could fail.
Right.
You got F out of the equation, but that inequality still has a limit on this.
True. This is still a constraint on here. By the way, what would fail in these equations if it started to slip? Because I cranked it up so the slope was too steep or something like that, so that friction couldn't keep it rolling, then alpha would no longer be A over R. That's for the perfect rolling condition where the velocity of a point on the rim is related to the angular velocity by E equals omega R. So where are we? I was going to copy that formula. A. Here's the formula for the acceleration of an object rolling down an inclined plane. By the way, if it slid down without friction, would it go faster or slower than rolling? Faster. Is that surprising? Faster because for that case, there's no friction by definition. The friction is holding this thing up. If it were sliding without friction, it would be G sine theta. That was the old formula that we got a long time ago for sliding down an inclined plane. But in fact, it's not that. It's that over 1 plus I over mr squared. And that means that the acceleration is somewhat reduced by that factor in the denominator. Let's do some examples. What are moments of inertia that we know about? Who? I equals, you tell me, for a hoop. When you should always hope for mr squared, because all of it's on a radius r. Mr squared. What does that mean? The denominator is 1 plus I over mr squared is 1 plus mr squared plus 1 plus 2. So the answer is A equals G sine theta over 2. That's for a hoop. A hoop rolls down there with half the acceleration that a frictionless block would have had. How about a cylinder? Here's your cylinder. Remember the moment of inertia of a cylinder? Remember it? It's a half mr squared. So this quantity is now 1 plus a half mr squared. 1 plus a half is 3 halves. And that means that the acceleration of a cylinder would be, that's in the denominator, at 2/3 G sine theta. Which one's faster? Cylinder goes faster than the hoop does. The hoop is really, for a moment of inertia, you're getting a mass out as far as you could possibly get it. So that's a big moment of inertia. Here's the hoop and the cylinder. We'll run a race here. Who won? I was too much concentrating. Cylinder went faster. 2/3 is bigger than 1/2. Sure. Spheres. I equals, anybody know it? This is the weird one. It's 2/5 mr squared. So the factor here is 1 plus 2/5, which is 7/5, which means that A is equal to 5/7 5/7 g sine theta. 5/7 is a little bit bigger than 2/3. Yes, it is. Check it out. Put it on your calculator. A sphere is going to roll faster even than that cylinder does, and a whole lot faster than the hoop. So, sphere is supposed to go faster. It did. On the other hand, you might notice that the radii all canceled out of these things. The radii and the mass canceled out. So it shouldn't matter for an object of a given shape, the speed should be the same regardless of how big it is. So let's run two spheres against each other. It's hard for me to start these off perfectly equal. I think that kind of did it, didn't it? And here are two cylinders, block of wood and aluminum, same shape, same moment of inertia, same formula for the moment of inertia, so they should roll the same, and they did perfectly. So the different objects roll at different speeds according to their moment of inertia. Biggest moment of inertia means largest factor in the denominator, the thing rolls slower. By the way, if all you are interested in knowing is how fast they're going when they get to the bottom, you might use conservation of energy instead. How would that go? mgh is the gravitational potential energy that it loses when it goes down there. That's converted into two forms. Translational kinetic energy, 1/2 mv squared, plus rotational kinetic energy, 1/2 I omega squared. On the other hand, if it rolls, omega is equal to V over R. So mgh equals 1/2 mv squared plus 1/2 I times v squared over r squared. I'm trying to find the velocity that this thing has at the bottom. So let's factor out, in fact I'll factor out 1/2 mv squared while I'm at it. The first term is just 1/2 m, I'm going to have to put an m in the denominator, and v squared, so it would be plus I over mr squared. That same factor, I over mr squared. So cancel the m's, multiply through by a 2, divide by the 1 plus I over mr squared and take the square root, and I would get V is equal to the square root of mgh, not mgh, the m's out of it, gh over 1 plus I over mr squared. Did I do that right? To gh over that square root. There it is. So that does it if all you want to know is the velocity when it gets to the bottom, or for that matter, if it were some kind of a complicated roller coaster track and you wanted to know how fast is the thing when it gets down here, conservation of energy. But remember, there are two forms of energy here, kinetic and rotational. Yeah. I did. Ah. That too there. Yeah. Good. Okay, enough on rotation.